So the next talk is by Dani Figueroa from TIC in Valencia. And whenever you want, the early universe is yours.
Thank you very much, Guillermo. Thank you very much for the organizers for inviting me here. I think this is actually my first in-person workshop since the pandemic. I'm really enjoying the discussions and having people around. And let's see if I have something interesting to tell you about the early universe in a quite generic manner from a numerical perspective. This is what I'm going to address. So the early universe, by this I just mean the very first second of the universe, including inflation, reheating, and the thermal era before BBN. And what's interesting about the early universe is that there are a bunch of phenomena from curvature fluctuation to particle production, like what Michele was describing, to phase transitions or possible cosmic defects, all of which might be very different among themselves, but however, they do share something in common. And this common factor is that is the fact that in many regimes, they are characterized by nonlinear field dynamics. If you really want to address this dynamic, you need to deal with the nonlinearities of these systems. And this goes not only for these phenomena, but of course it goes for the consequences of these phenomena, such as production of gravitational waves, realization of baryogenesis, magnetogenesis mechanisms, or black hole formation. And of course, if I want to go a bit more non-canonical, I can also address other interesting problems, such as the dynamics of non-minimal gravitational sectors, non-minimal kinetic theories, or very interesting but complicated problems, such as turbulence or thermalization. All of these are typically characterized, or in many regimes, by nonlinearities. So if there is one message to take home, which I would like you to take home, is the following. There is a new guy in town. His name is Lattice, and he wants to become your friend. So if you want to become friend to Cosmolizers, you can do this in an easy manner. You can read our Lattice theory review, where we explain all the techniques we use, or you can jump directly into the manual of our code. What Cosmolizers will do for you once you become friends with it is the following. It will allow you to simulate the scalar gauge field dynamics, including abelian and non-abelian, SU2 in this particular case, for self-consistent expanding variables, so as sourced by all those matter fields. It's written in a modular manner, such that we separate pretty much the physics from the technical details, such that if you are a theoretical physicist and you don't want to know nothing about the technicalities behind the code, you can certainly still approach to do very complex things without having to enter into the actual technical details of the code. It is parallelized, and this is very important, in multiple spatial dimensions, but you are going to write everything in serial as close as possible to the continuum equations of motion. But the fact that it's parallelized and this is hidden to you, it means that you're going to be able to run simulations in mega big clusters where you can separate as much as you want the scales of your problem. And finally, we've already given a family of evolution algorithms for different problems. So essentially, you may only have to choose from a menu which algorithm you want to use, and then you are kind of ready to go. For details, please have a look to our website. We have all kind of details here, including instruction, how to download, various documentation, different version evolution, events we associate to the code, etc. So what Cosmolizers does for you is the following. Imagine you have a physical problem, which is going to be characterized by a set of equations of motion, given whatever choice of interactions you want to simulate, want to understand, and by some initial conditions you impose into your fields. So Cosmolizers is going to put this initial condition setup into a lattice with a given number of points per dimension, a given ultraviolet resolution, the lattice spacing, and then essentially it's going to put the lattice in a manner that is going to be hidden to you. So all you have to choose is how many points per dimension you want, what's your lattice spacing, what's your time step. This will determine, of course, how slow you go in your evolution. Then you choose which algorithm you want to use to solve these equations of motion. And then, of course, you choose your physics, which is the strength of certain parameters involved in the model, given the interactions you have here. Then you choose your observables, and all of this is literally just one file where you, by flags, go choosing, I want to plot this, I want to plot that, I want to include this or that type of interactions, etc. Press play, and you get this kind of outputs. Three-dimensional distribution of your fields, if you are interested in that, two-dimensional slice, power spectra of various kinds, mean values, volume average of, like for instance, mean value of a scalar field, etc. All right. So the idea of Cosmolizers, what I want you to understand, is that this is a code which is very generic. So you should try to understand this code as a platform. It's a platform for field theories. Now, if you have a problem in field theory, for instance, the ones that Michele was discussing before, and you know your dynamics is going to become nonlinear, then your analytics is going to become very complicated. However, with a platform like Cosmolizers, you are now capable of solving it, including the nonlinear regime. And the idea is whenever you have a new physical problem, in principle, if you are capable of writing the equations of motion in the Lattice language, then you can solve this problem with a platform like this. So what problems can we solve? I'm going to mention that in the next slide, sorry. What Cosmolizers so far does in the public version is it's capable of simulating global scalar field dynamics of any kind, no matter how nonlinear your potential is, a billion Higgs type of dynamics, so gauge U1 gauge invariance systems, and non-abelian with SU2 gauge symmetries. We do this in the public version so far for canonical kinetic terms, self-consistent evolution, homogeneous initial conditions, for instance, a homogeneous inflaton, on top of which you can put quantum fluctuations. But Cosmolizers is rapidly evolving, and we are already preparing the release for next year, which is going to include now the ability to do gravitational waves from any matter sector you simulate, let it be scalars or gauge fields. We are going to include action-like interactions of this kind. We are going to include non-minimal gravitational interactions, and also the ability to evolve, for instance, or to simulate cosmic defect networks. It's going to come with evolvers to deal with non-canonical kinetic terms, which are still under work, for which you need non-symplectic integrators, which we already have working, but we just haven't tested well here. And it's going to do all of that, again, always in self-consistent evolution of the universe. And it's going to allow now for arbitrary initial conditions, essentially whatever the setup you have. Since there is so much interest in gravitational waves, we already released the module to do gravitational waves from a scalar sector. That's already available. So if you want to compute gravitational waves from a scalar sector dynamics, you can already do it with the version available public. All right. What kind of applications can we consider with Cosmolizers? Well, there are plenty of things I can think of, no? It can range from preheating dynamics or equation of a state after inflation to gravitational wave production from whatever nonlinear dynamical system to inflationary dynamics during a nonlinear regime, evolution of the cosmic string networks, which could be interesting for axionic strings or for a billion Higgs strings, dynamics of a single loop, isolated, dynamics of scalar fields which are non-minimally coupled in to gravity, but you still remain in the Jordan frame. You want to understand it there. Phase transitions and alarms, etc. Of course, because time is finite, I'm going to show you only 3 examples, which I'm going to number now 1, 2, and 3. And the third example only if there is time, which I'm not sure. So the first example, it's going to deal with gravitational wave production from some interesting nonlinear dynamics. The second example is going to deal with inflationary regime, and I'm going to focus in action inflation. I'm going to solve a problem, actually, I think the community has been interested in solving for 10 years, and you could only do it with this kind of techniques. And if time permits, I'm going to show you some results about how a single loop from a cosmic string network behaves when you isolate. So, example 1. What I'm going to attempt to do in this exercise or in this example I'm going to cover here is to show you the ability that we may have in the future with gravitational waves to do particle coupling spectroscopy. So I'm going to try to reconstruct particle couplings from a given set of interactions with gravitational waves. Well, this is done, by the way, in collaboration with Nico Loaiza, which is sit down in the audience. It's one of my PhD students, and he's responsible for the simulations I'm going to show you here. So, what is the motivation for this? What do I mean by what I'm saying by spectroscopy of particle couplings? Well, it is known that preheating or non-perturbative dynamics in general, or strong first-order phase transitions, they generate a strong signal of gravitational waves. But typically, what you see or what this gives rise to is a single band spectrum. This is the spectrum of gravitational wave versus frequency today. Of course, in some complicated scenarios, people may have some structure here on the peak, but typically this is what you are getting. Now, what I want to address here is what's going to happen if I am in a situation of where I have many particles, okay, or at least certainly more than one particle coupled to the source of gravitational waves. So what happens if you are in a multi-particle system where all these guys are going to get involved into the production of gravitational waves? And the question I want to address is, can we reconstruct the particle interactions, the particle couplings, from the hypothetical direction of this gravitational wave pattern? So something like this. Am I going to have some kind of a spectrum in the gravitational wave background that has different features, spectral features, that if I'm able to recover them from detection, then I could tell something about these interactions in first place. I'm going to do this with a very simple scenario. Just this scenario is going to serve as a template for me to motivate the case, but in principle, this should be applied also to not just to this scenario, but to many others. So this scenario is very simple. It's an alpha tractor type of inflationary potential, which essentially means I have an inflaton potential that flattens out for large field scale and becomes a monomial potential at the bottom of it. For simplicity, let me just consider the quadratic interactions here, the quadratic monomial here, although this, of course, could be applied to whatever power you put there. So this inflationary potential is, of course, compatible with CMB scales. This is why you CMB observables. This is what you flatten out the potential here. And what I'm going to be looking at is the dynamics here, when the inflaton starts oscillating after inflation. It is well known that in this kind of preheating dynamics, due to the oscillations of the inflaton, this induces a time-dependent background to the fluctuations of this extra preheat field that I'm putting here. So I'm coupling this preheat field to the inflaton in this generic manner, and I have now, like Michele before, a time-dependent background where I can excite this preheat or daughter species. This is well known. I'm not going to dwell into the details of this. This phenomena, in this case, is called parametric resonance, and it gives rise to an exponential growth of the amplitude of the fluctuations of this daughter field chi, just because it's coupled to the inflaton, and it excites the daughter field within this range of momenta, which is typically an infrared window below a given cutoff. So the physics of preheating in general is the study of oscillator-like equations for the fluctuations of the fields that are enjoying the excitation, which correspond to scale and time-dependent oscillators. And already in the linear regime, this you can solve typically exactly, but the physics is already complicated because the physics corresponds to an excitation that is non-perturbative and is out of equilibrium. Okay, which is really that infrared window that I was showing before of the power spectrum. But what is even more interesting is that once you pump sufficient energy to these daughter fields that you are trying to use to reheat the universe, the system is going to become fully nonlinear. Because if you pump too much energy, they are going to talk with the source, which is the inflaton, and the whole system is going to talk to each other, hence becoming nonlinear. And hence, this becomes very difficult to address it analytically. What's going on here is essentially at a specific range of momenta, the amplitude of the fluctuations of the unstable fields grow exponentially fast. This only happens for a finite range of momenta. And if you translate that into real space, this corresponds to large inhomogeneities with large high energy density contrast that propagates at the speed of light. So essentially, a very, very good source of gravitational wave production. This is why preheating is a very good generator of gravitational waves. There is a bunch of many papers that many years ago were taking care of this. I'm not going to dwell into the details of this. I just want to highlight that if you want to study that properly, because the system, the dynamics becomes nonlinear, you need this Lattice simulation. So, in these scenarios, people have studied that when you have a monomial shape at the bottom of your potential, you do parametric resonance of your preheat field, and this generates gravitational waves and gives to this kind of single peak spectrum. There is a maximum height. This is the spectrum of gravitational waves. The fraction, if you want, the spectral fraction of energy density of gravitational waves versus appropriately rescaled momentum. And there is a single peak with a height and a location. And people have parameterized the physics that controls the shape of this spectrum as a function of the resonance parameter, which is the parameter that controls everything. This is a dimensionless parameter that it's built from the strength of the interaction between the inflaton and the dotted field, from the initial amplitude of the inflaton, and from the curvature of the potential of the inflaton. So essentially, people like myself and former student Paco Torrenti, we parameterize these backgrounds, and the amplitude is really controlled by what's the strength of this resonance parameter. And of course, the position also depends on the strength of the resonance parameter. So now, what I want to highlight is not how big is the amplitude, which is the typical studies that people have done in preheating scenarios. What I want to highlight is that if you notice in the parametrization, what I'm saying is that the amplitude of the background scales inversely proportional to the resonance parameter, which means inversely proportional to the coupling, to some power. And the frequency, the position of the peak, it also scales linearly with the coupling in this case. That immediately should make you think, okay, what's going to happen if I now have multiple species coupled to the inflaton with different coupling strengths? No? Essentially, if I have such a situation, the question is, can I do, through observation of the gravitational wave background, the inference through a spectroscopy analysis of what are these couplings? No? Am I going to have some sequence of spectroscopic spectral distortions in my power spectrum of gravitational wave? Well, if this is the single peak spectrum from a given situation where I take the the alpha attractor type of inflationary potential, and I consider a single preheat field with a given coupling strength, it's going to give me this for the gravitational wave spectrum. If I do a second simulation where I consider the same scenario, but I consider now that the dotted field, there is still only one, has a larger coupling. So essentially, what I'm going to get from this single preheat or dotted field simulation is another spectrum of gravitational waves coupled, another spectrum, peak at a different frequency. Now, the question I want to address is what happens if I have two preheat fields? And in reality, the answer is kind of obvious. What you're going to get if you simulate this system where you have two preheated species with different couplings is you're going to get a gravitational wave background that now has a peak structure reproducing the previous peak locations when you had a single preheat dotted field. And why is this interesting? Because it is precisely the location of these peaks that is going to give me the ability to reconstruct the couplings. So let me show an example, an animation that actually Nico did for a case now for three couplings. You can guess what's going to come out, but just to show it. This is the spectrum of gravitational waves, again, at the time of production versus momentum. There is some noise numerically, initially in the spectrum of gravitational waves, but as we go with the parametric resonance process of all the three species, what we see is that we start recovering a three-peak structure in the spectrum of gravitational waves, with the dashed lines predicting a priori, because this is based on the single dotted field spectra, the location expected to emerge for these three peaks. So another picture of this, the evolution in time is this. We have three peaks in this case, and as you can imagine, this would generalize to as many peaks as different preheat fields you may have. So we call this a stairway signature for obvious reasons. We try to call the paper Stairway to Heaven, but the editor, as usual, didn't like it. In any case, well, I hope you get the idea. It's pretty simple. What I'm going to show you now is a demonstration that this kind of signature could be reconstructed with experiments like the next generation of experiments like LISA. So for simplicity, I'm going to do it with a two-peak signal. And we are going to consider a signal of this kind, with this two-peak structure, that is placed at the LISA frequencies. Of course, in order to do that, I should do it with another scenario different than the one I show you, because typically this kind of spectra are really peak from that scenario that I'm simulating are peak at high frequencies, not at LISA frequencies. But let me shift by hand and understand this spectrum as a template for potential scenarios that would have the same kind of physics, but would produce a peak in the observable frequencies of LISA. So imagine I just translate my spectrum of gravitational waves. I have redshifted it today, so this is the amplitude you really get from the redshifting, and I just place it in the middle of the LISA sensitivity. And here we inject it into our simulator to see with the noise of LISA, which is this curve here, if we will recover it. And in orange, on top of the red line, so the red one is the theoretical one, input from the simulation. The orange points is actually the reconstruction. And you can see that using for this kind of amplitude, we can really reconstruct very, very well the two-peak signature. If we do the same exercise for the futuristic experiments such as BBO, then the reconstruction is just perfect. Within the whole range of frequencies, you don't even see the input signal because it's below the points I'm reconstructing. To quantify this a little bit more, so we do a Monte Carlo Markov chain, and then what we can tell is that the position of the peaks is reconstructed very well to better than 1%, and this translates into a reconstruction by master formula how to relate the peak position with the strength of the coupling. This translates into reconstruction of the couplings. So I highlight it here. For the first peak, we choose this coupling, and these are the different reconstructions, always compatible with the original input for LISA, BBO, and other hypothetical experiments. And for the second coupling, so on and so forth. Okay. So with maybe two large errors, what we are showing here in any case is that it's going to be possible in the moment you start analyzing signals that come from multi-particle systems to really do particle spectroscopy. Unfortunately, for the scenarios Nico and I we were using and our collaborators, the physical signal is really peak at gigahertz or just slightly below that, for which, well, there are no good detectors prospects for this kind of this background, unfortunately. So you should really take our example as a proof of principle. Obviously, I just want to highlight the ability we are going to have in the future to do this kind of aspects. There is hope for other scenarios, of course, because nothing prevents me now from taking multi-particle systems, say in a low-scale preheating scenario. That's something Nico and I were working on now, or in phase transition, for instance, at the electroweak scale, that would peak naturally at the LISA frequencies. Good. This is a possible door to particle physics using gravitational wave backgrounds. And I think it's very relevant to realize that you see sometimes most of the analysis that people are doing with all the scenarios that people are considering in the literature, the reconstruction of the actual microphysics parameters of the scenario are very blurry, no? Because, for example, if you look at a phase transition, you have a bunch of general parameters like alpha and beta, but you don't know about the microstructure of the phase transition, like the couplings of the different species. And what I'm saying here is that in the moment you add this coupling of multiple species, imagine certain gauge fields coupled directly to the Higgs in a phase transition, you are going to get this multi-peak spectra, and we are going to be able to deduce, in principle, if we can detect that signal, what are the couplings of the microphysics. Okay. Good. And of course, there is still the possibility, as Diego was mentioning, that perhaps in the future, evolution of high-frequency detection evolves, becomes better, and then, well, maybe we have a chance also at high frequencies, not only at LISA or next generation experiments. Good. Is there any question here? Yeah.
Okay. Can I see the time evolution again?
Like this one?
Yeah, maybe this is a stupid question, but the initial condition, there's already some amount of gravitational wave. Does it come from the fluctuation with the scalar field?
Yeah. No, but initial condition is probably way down here, you know, and it's just noise. Yeah. We start with 0 initial condition, and in the first time step, I evolve the scalar fields. They are already slightly excited, the gradients of the scalar fields, and it gives some noise here. Okay, but it's way suppressed these scales. So all this process, this growth coming exponentially, comes from the parametric resonance exponential growth of the scalar sectors. Yeah.
Okay, thank you.
No problem. Any other question?
Again, maybe it's stupid, but how robust is this to the presence of coupling between daughter fields?
It's not robust, and that's a very, very good question. Of course, here I've been very simplistic because I'm not considering couplings between them. But what is interesting is that if you start adding genetic couplings, say quadratic, between them, it turns out that what we are observing, although we are not sure to do a paper about this yet or not, but what we have observed is that modulates the relative heights of the peaks. So it's amazing, in a sense, analogous to CMB and isotropy spectrum, that depending on the ingredients, you really may have an outcome different from which you can infer what's the strength of those cross interactions. The difficulty is that compared to CMB analysis is linear, and this is not, you know, so it is a very difficult mapping to do, but certainly we've seen this kind of effects, that if the couplings in between species are negligible, you reproduce the same structure. If they start becoming sizable, they start modulating or even making disappear one of the peaks, you know. So, yeah.
I wanted to ask the same question.
Everybody wanted to ask the same question.
No, okay, so I'll go first. Yeah, I mean, first, it's a general question. Maybe I should have asked it at the end, but I don't know. And also, forgive my ignorance. I mean, just like, so I'm interested. My question is about really how you are doing these things, you know, the level of the code. So you're saying you have this Lattice code,
yeah.
Which, I mean, of course, it has to be classical. I mean, you cannot put quantum stuff in there.
Yeah.
So my question is more on the quantum side. I mean, how do you do the quantum calculations?
Yeah.
In which sense?
What is quantum? What is classical here? Yeah.
So
the quantum mechanics here, what matters is to set up the initial condition, the initial fluctuations of the daughter fields. So these daughter fields, you can think of them as quantum fields initially. They have a spectrum of vacuum fluctuations. Vance-Davis, you know, the standard quantum mechanical vacuum for the modes inside the horizon. And it is because those modes are present that then parametric resonance starts taking place. Okay? So if it wasn't because of quantum mechanics, there would not be parametric resonance. Despite the fact that parametric resonance is a classical effect, it requires a quantum initial fluctuation condition.
That I understand, but the fluctuations are then classical, right?
Yeah, and then the way I introduce them is I introduce an ensemble of classical fluctuations which mimic the quantum spectrum.
I see. So you do not really see the quantum to classical transition kind of thing.
No, you do, because the point is you can compute the occupation number of that spectrum, and you see as it grows exponentially, you can see how the bigness function, for instance, squeezes in one direction, and you can see how the occupation number becomes exponentially large.
Okay,
so you do see that. But the funny thing is, initially, I introduced it still as a classical ensemble mimicking the quantum fluctuations. Okay, still, that should be not correct, but in practice, it really reproduces the quantum physics. If you compare with your quantum mechanical analytical computation, you get the same in the linear regime as doing this.
Is this explained in one of your papers?
I think it's explained in the original papers of preheating late 90s. I can give you the exact references. Yeah.
Thanks a lot.
Yeah.
No? I can wait till the end.
Okay, very good. So, thanks for the questions. It is a very relevant question, that, because it always confuses people. I can elaborate further in detail if you want in private. If you want. Now, second case in which I'm going to apply my technology, my Lattice technology. It's a problem that I think has interested a lot of theoretical cosmologists, which is what is the dynamics of axion inflation? What is the dynamics to the full extent of finishing inflation in the nonlinear regime? So let's see what I mean by this. So axion inflation is just a label for the scenarios which you invoke a shift symmetry. So you can have your, for the inflaton, so you can have your inflaton coupled to some FF dual operator of a gauge sector. I'm gonna just take a gauge abelian sector, a dark photon. And well, assuming there are some non-perturbative effects that provides a potential that breaks this symmetry, then you can, in principle, do inflation. And what people have done is to study what is the dynamics of this dark photon in these scenarios when you have this shift symmetric coupling for various different potentials. So essentially, if you study the linear level, the evolution of your, let me call it photon, no? The photon has two helicity. What you immediately realize is that the two helicities are different from each other because this is a chiral coupling, and this is manifested in these two different signs here. This immediately means that one of these modes is going to be tachyonic during inflation, and this is why people were interested in studying this, because that amounts to have a continuous excitation of this guy during inflation, of one of the polarizations. And the whole effect is controlled by this parameter psi, which is a way of measuring the velocity of the inflaton in some interesting units. Okay. Right. So people have studied this. There are dozens of papers of this. And one of the first things that people realize is that, of course, this is going to give rise to non-Gaussian scalar perturbations, simply because you have this kind of coupling. So essentially, the excited gauge fields are going to source scalar fluctuations through inverse decay process. And of course, you are going to have to be careful with the couplings you assume in your theory if you want the decay constant here, because you need not to violate non-Gaussian limits from CMB. Even more interesting than that is that since you are going to excite a lot gauge fields because they are going to enjoy an exponential instability through the tachyonic mechanism, you are going to excite also very abruptly the scalar perturbations. So if you go to a smaller scale than the CMB as inflation goes, you are going to excite them so much that you can be in situations where the excitation, say here I'm plotting the power spectrum of the curvature fluctuation, it violates PVH limits. Okay, it violates basic limits that we know cannot be violated because we haven't seen such a density of primordial black holes in the universe. And of course, the problem of inferring any information here is that all these computations are done in some analytical regime. Let me not enter yet there. Let me continue with the physics. The physics is not only interesting because of the PVH production, also you are going to produce a beautiful gravitational wave background, which furthermore is going to be chiral. Just because you are going to excite exponentially your gauge fields, they are going to have a non-trivial transverse traceless path, which is the source of gravitational waves. So all during inflation, you are going to go exciting these gravitational waves, way above the vacuum fluctuation contribution. Now, as the gauge field excitation depends exponentially sensitively to the velocity of your inflaton, the signal of gravitational wave is going to be very sensitive to your choice of potential. So here is a paper by Valérie Dom and collaborators a few years ago, where within certain analytical approximations, they explore various different potentials and note how different the gravitational wave signal is going to be. Both gravitational wave production and non-Gaussianity are going to be constrained at the end by how big your coupling you can tolerate in the axial coupling. So essentially, for a monomial potential, PVH bounds, in principle, PVH bounds, so saturating this PVH limit here, prevent you from having presumably observable gravitational waves in certain scenarios. There are other scenarios, however, where according to these bounds, I'm still compatible, presumably, with my gravitational wave spectrum versus frequency today to be within, for instance, the LISA sensitivity curve. And this is very interesting because if this is really the case, it means that if we measure this background with an experiment like LISA, we'll be able to infer information directly from inflation. Okay, something that, of course, the quantum fluctuation background cannot do. And furthermore, this is a very blue tilt background, chiral and non-Gaussian. So it has a number of features that makes it very special to distinguish it from other backgrounds upon detection. But now the question is, can we really detect this background? Is this really realistic, this prediction?
So what is this? Another choice of potential?
This is for a specific choice of potential, the m squared phi squared. If you take into account the PVH bands, you are still capable in principle of producing this. In the other plots I was showing, they were choosing other potentials. So it really depends on the potential, the answer. That's the problem.
Sorry, then.
Yeah,
Isn't this already excluded by LIGO, or do I read wrongly the scale?
No, I think it's not excluded by LIGO because we did this 5-6 years ago. So the lower bounds of the stochastic background from LIGO are coming down, but as far as I remember, it's not really touching this yet. But if it was, you are right, then I should still choose a slightly smaller coupling and so on and so forth. Okay. But what I really want to address here is what I want to highlight is the following problem. All these computations from primordial non-Gaussianity, gravitational wave production, and PVH, which is, if you want, the study of the scalar fluctuations, have been done with analytical approximation. For a simple reason, it's very complicated to deal otherwise with nonlinearities. But let's have a full look into the problem. Let me, in order to do this, define some variables, conjugate momentum of my scalar field. I'm going to call it pi, electric field, just this, magnetic field. For convenience, I'm going to conformally rescale my electric and conjugate momenta of the scalar field like this, which is the tilde here. And I'm going to call my scale factor derivative pi a. So if you write down the dynamics, the equations of motion, in the full theory, okay, including everything, this is the evolution of your inflaton sector, sourced by the gauge fields here, and this is the evolution of the gauge sector, sourced or coupled, if you want, to the scalar sector through these two terms. And on top of this, of course, you have to do it self-consistently, following the expansion of the universe self-consistently. So the evolution of your derivative of the scale factor, the Friedmann equation, has to be given by the contribution at the larger scale, the expectation, if you want, of the kinetic potential, electric and magnetic energy density. So what people did is that, of course, they realized the system will become nonlinear because there is this coupling, so the system is going to be a system of coupled differential equations. And once you pump a lot of energy from one to the other, there's going to be back reaction and so on and so forth. So the system becomes nonlinear. So the first approach that people took, for instance, Lorenzo Sorbo and collaborators more than 10 years ago, well, they said, let's be in the homogeneous regime. We eliminate anything related to gradients, and let's neglect, for the time being, just to understand the effect, the back reaction of the gauge fields into the scalar, and we focus in this interaction. And when you do that, you immediately realize this tachyonic growth that gives rise to exponential growth of the gauge fields. Fantastic, okay.
Sorry, I'm a bit confused.
Yeah.
So you have A dot, but then you have gradient, so it's a function of x and t.
So are you talking about
the first equation before you cross that term?
Yeah.
So the right-hand side is a function of x and t.
That's correct.
And the other one is just function of t.
Well, only the expansion of the universe, yes. We are doing the Friedmann equation.
But you should not average something
here? Well,
no.
In principle, not. I'm looking for the inhomogeneous. Well, I'm going to look for, that's what I'm going to show you, the inhomogeneous dynamics of these matter fields in a Friedmann-Lemaitre-Robertson-Walker background metric dictated by themselves. You know, that's the idea here.
I guess this is okay as long as they don't become super large.
No, actually, they will become super large. This would be okay as long as the scalar or the metric perturbations don't become super large, which would spoil the fact that I'm ignoring them because I make them live in a background sourced by themselves. Okay, but the key is the metric perturbations.
So when you write the Friedmann equation, you are assuming that the universe is homogeneous. So then I would average all the quantities that depend on x.
No. The thing is, what you are assuming is that over a certain scale, you know, there is an average contribution from all of these guys that is making a space-time background. And of course, on top of that, locally, you have perturbations of your metric, which I could solve separately, you know, but I'm not doing that. Okay, that's the idea. yeah, to do it consistently, I should include those perturbations, okay? But poc a poc, they say where I live now, okay? So here what I wanted to emphasize is that people started studying the exponential excitation of the gauge field through this interaction, become clear that, it's exponentially excited, and that's very interesting. In the linear regime, they even ignore the back reaction of the gauge field into the expanding background. But then, okay, let me put for convenience these variables here. It became clear, that if you want to study this system, once you pump so much energy into the gauge field, you really need to deal with back reaction. So essentially, in order to deal with back reaction, this is a difficult problem, no? Because how do you do it? No? And what people decided to do is to take the homogeneous approach. So essentially, they take expectation value of the source for the inflaton sector, and they keep eliminating the gradients here, the Laplacian, and the cross term here. And of course, you can do this because, these expressions, the E dot B, or the electromagnetic energy densities, you can take these kind of expressions, which is going to give you these contributions. Okay, fine. So you can really study back reaction in this homogeneous regime. People have done it, have studied this evolution on the one hand without this kind of term. And of course, the problem of this is that this amounts to a very complicated system of equations, because every time step you do to evolve these gauge field fluctuations, now you have to go back to these expressions, compute them, back them here, make a one-time step of the scalar sector and the expanding background, and then so on and so forth. All right, so these were very elaborate iterative schemes that take, of course, very long to run. People came with a clever idea last year, which is the so-called correlated gradient expansion. I'm not going to explain it, just saying that they rewrote the equations in terms of correlators, and then they managed, within this homogeneous back reaction approximation, to write the same physics, to obtain the same physics. Can we do better than this? Well, the answer is kind of obvious, no? Given that I'm giving a talk with, about a code that can do inhomogeneities and nonlinearities in full detail. But we need, of course, a full lattice approach to deal with this, which is not simple. First of all, let's restore this equation in this form. And secondly, let's restore all terms, because I really want to balance energy conservation and so on and so forth. So what I'm going to address in the last 5 minutes I have is how to do the fully inhomogeneous back reaction of this system. Okay, the question in order to do that is how to lattice the system of equations of motion, and this is not easy at all. I'm not going to dwell into the details. I'm just going to tell you that it turns out that by chance, with Misha Shaposhnikov, I had addressed this problem in a completely different circumstance, nothing to do with axial inflation, but we did have a formalism that actually allows to write in the lattice a shift symmetric coupling phi FF dual. Without dwelling into the details, just to tell you that this lattice formulation is gauge invariant, respects Bianchi identities, and the most important thing, the topological term of FF dual, is really a lattice derivative of a Chern-Simons current, which is the underlying basis to call this a shift symmetric coupling when you couple FF dual to phi. Okay? Just to show you some comparison between the lattice and the continuum equations. So this term here represents the source for the scalars. This term here represents the interaction between inflaton and magnetic field. This one here, and this complicated, the system has gone rogue. And this complicated term here represents this cross term here that every single study has ignored until now. Okay, then you put this in the lattice in an expanding background where now you have to add all the contributions, kinetic, gradient, potential, electric, and magnetic field contributions at volume average to dictate the expansion of the universe. So what I'm going to show you now is a bunch of plots which are work in progress. I'm going to focus in this particular coupling because this is in principle compatible with the analytical estimates from PVH, taking this simple potential, so I can compare with the literature. If we were in the linear regime, so inflation physics is dictated by the inflaton alone, this will be the end of inflation. There is a breaking of a slow roll eventually, and here you stop counting your foldings of inflation. What's really happening in this system, at some point you produce so much gauge fields that they are going to backreact in inflationary dynamics, and the actual epsilon parameter that controls the end of inflation actually goes like this. It bounces and then goes up, like extra 4 e-folds after what you would have thought was the end of inflation. So first message, you are getting extra e-folding during inflation, and you are going to be dominated by gauge fields, not just scalar fields. If I analyze the spectrum of gauge field excitation, this is the polarization of the tachyonic mode. We start in Banch-Davis, and what you see in these lines is that as I go in linear inflation, in linear regime, I'm going to end inflation, and this would be the very large excitation you had of the gauge field. But if you plug in the nonlinearities, in reality, the excitation starts to be not as large, because here I'm above the full system for the tachyonic mode up to the same number of e-foldings. But what we found before is that there are extra e-foldings, okay? So this would be only the end of linear inflation. In reality, the system continues until the real end of inflation. But look what it does here. Excites orders and orders of magnitude more within the nonlinear regime, the gauge field, plus it displaces the peak of excitation, following the horizon as we go on with inflation. Furthermore, this system is known to be very chiral because only one polarization is tachyonic. But this breaks down a little bit now towards the end in nonlinear regime, because if I plot you the total gauge field with the two polarizations and the chiral and the tachyonic one, you see that there are differences, okay, between the continuum and the dashed lines. And the reason is because the cross term with the gradients of the scalar is actually exciting the other polarization. So one of the most famous predictions of this scenario is that it's fully chiral, and what we are realizing here is that this is not the case once you go fully nonlinear. And you reduce the chiral imbalance actually a lot depending on the scales you look at. This is just a zoom, just to show you that we have very well under control inside the lattice. The spectrum is just the same. What's going on, if you look at the energy densities, here the total energy divided by the different energy components by the total one. In the linear regime, you see the electromagnetic energy density you are pumping goes like infinite, no? Because you are stopping inflation, ignoring this. In reality, there is a back reaction, and you are going to saturate that growth, but that's going to impact in your kinetic energy of the inflaton, and essentially you are going to end inflation now dominated by the gauge field sector. If we look at the psi parameter, well, this is the important parameter in order to compute all the observables, and essentially this is what you would have done in linear regime, and however, this is what it really happens in the inhomogeneous fully nonlinear regime. If you compare to the homogeneous approach of other people, both the paper of Valéry-Dom or the paper of the gradient expansion, you see that the homogeneous back reaction still gets some feeling of what's going on, but it really is really different. And the problem is that your physics is exponentially sensitive to this parameter. Okay? So because Guillermo is telling me I should be finishing, I'm gonna skip other results for this other coupling. And I'm just gonna highlight the conclusions in this scenario. So essentially, psi parameter, which depends on the velocity of the inflaton, controls the gauge field excitation. Any small linear change in psi turns into exponential change in the gauge field. Once this becomes nonlinear, of course, it's even more difficult to make this relation. But all predictions and constraints have been made about primary non-Gaussianity, PVH, and gravitational waves, especially these two that happens at shorter scales, depending on estimations of psi, which were done with these crude approximations of the homogeneous back reaction in the best case scenario. So now with this code we have, we can reassess the real observability. We can even add Swinger pair production through effective conductivity, and then re-explore all the baryogenesis or magnetogenesis phenomena associated to this scenario. Soon in the archive, hopefully before Christmas, that's my hope, I'm gonna skip this because otherwise Guillermo is gonna kill me. And then I'm gonna just thank you. If you want to know more about our code, please visit our website or have a look directly if you want yourself, or put your PhD students at that into our review or our manual of the code. Thank you very much.
So when you're looking at sort of like these, simplified theories like this last one, this axion inflation, at precisely the time when these nonlinearities are starting to become important, I would expect that that's around the place that this effective theory is breaking down. Yes, and so you're doing some numerical simulation. You have some check, internally that locally you're not actually violating. The terms of your EFT, that your occupation number is not getting so high that the theory is not the right theory at all. Really, you have to include.
We haven't checked that. We haven't checked that. Okay, we haven't checked that.
And this is just true.
On the other hand, I think the idea precisely of doing axion inflation is because invoking to a shift symmetry, you are in principle protected from corrections into your potential. So the fact that you have a lot of excitation, I think it only has to do with how you balance in the energy budget, whether there are more gauge field domination than the scalar sector and vice versa.
You have the cutoff, F, right? If I have, if things are getting above 4 pi F, then I need to take into account the thing that gave rise.
So in terms of momentum, this is okay. In terms of amplitude of gauge fields, that I'm not sure. Okay, I haven't checked nothing in that direction.
It's not just for that thing. Is if you put in your favorite theory in preheating, that's going to be some sort of effective theory, right? And so I guess it would be good to make sure that there's some check internally that whatever you're doing, that the result you get is not an artifact of having violated the.
Sure. But what with a shift symmetric field? So what other effective terms would you think that could induce?
Just other terms suppressed by higher powers of lambda, just other higher dimensional operators that I would write down.
Right. So you would just write down this and check if the amplitude of my matter fields is not so large that I would need to include them. We haven't done this.
It doesn't we haven't done include the other terms that would be there, then I guess I'd feel a little bit more safe. But
okay,
that's what I would.
Point taken. Thank you. We will have to think about that.
Sorry. Now if you have a lattice, I was wondering if it's possible to actually impose different boundary conditions. Can I do that if I want to?
Well, here we are doing periodic boundary conditions because you want to mimic the infinity of the universe.
But you don't want to do that.
If you don't want to do that,
non-trivial topologies, for example.
You can. In principle, you can impose whatever you want, but then there's going to be a very clear time scale of propagation of your modes that at some moment are going to meet this boundary. And that's the end of your simulation, because those are going to be artificial boundaries. So yes, you can do fixed boundaries, and for certain problems can be very interesting. But for this kind of out of equilibrium dynamics, typically that's not what you need. You rather need to mimic that you have a volume sufficiently large to encompass all the wavelengths that you are.
But you have that as a possibility.
You can do with you see. It's a matter of how you choose your equations of motion and your boundary conditions, both in time and in space. You can choose that.
I have lost it too. You're doing it.
Yes. We are not doing it yet because time is finite and takes time. And I keep being asked about this, but yes, we will do it. It's in the queue of things. But I think first, you see, this a billion case. It's so rich in phenomenology that people have worked out spanning 10 years. And the implication of this inhomogeneous dynamics in inflation, it really boils down to say that all observability or constraints of this scenario needs to be revisited. So we are going to do this first. And then if time permits soon enough, we will start with the...
Very good. Because, there are claims that the gauge-to detect reaction should be mined there.
Well, I think that makes sense because non-abelian theories become nonlinear even at the level of interaction of the gauge field. That's going to suppress excitation. But still, what is the phenomenology that you guys have worked out so much? possibly is going to need revision from this. It depends how nonlinear the system really becomes.
On the one hand, I want you guys to do it because I'm curious. On the other hand, maybe not because I want to change our predecessor.
Yeah, but Selavi, you know. Sure, I understand.
I had the very same question.
Yeah. So
maybe I have a very different question.
Okay.
We talked about applying something like this to what people call Higgs explosion.
What is Higgs explosion? Sorry.
There is some claims that in theories such as the standard model, more in general scalar theories, scatterings with many
many diagrams, they blow up.
With many final states, they behave.
No, it hasn't
no, because
crossed my mind.
The system.
Not even sure if we would capture the same physics,
No?
you know, and not even sure because very often with the lattice, we are capturing non-perturbative effects that you cannot really put in a series expansion of your coupling.
Yeah, exactly.
So
the point is that this will require something non-perturbative.
Yeah.
So,
well, I haven't thought about it, but
I don't know much about it.
I would need to think about it whether it's possible, feasible to represent such a case here. Yeah, I'm completely sure. Enrico.
Yeah, I have two questions actually. So on the lattice side, when you say you evolve the equation of motion self-consistently, and particularly the scale factor.
Yeah.
You mentioned the metric perturbation.
Yes.
Those, can you add the metric perturbations or not? Or
So
if
I wanted to deal with the full view, which is addressing, if you want, the first question of Michele initially, that would require a full GR code, where I solve the space-time metric locally. Okay, and those are Einstein equations. Okay, full Einstein equations, which would become very nonlinear, of course. Now, what we do in cosmology, as we all know very well, is that we divide our space-time metric into a background, sourced by everything, you know, in a sense of average over certain scale, plus metric perturbations. As long as your metric perturbations are under control, in principle, you believe this is splitting. So what I can do is to simulate the equations that control this metric perturbation. As a matter of fact, the gravitational wave module that Nico and my other student Jorge have worked out, it actually does that. It's following the tensor perturbations. But now if you want the back reaction of them into the matter fields, it's doable, but has to be written down and work out the latticization of the system in a correct way. And the same could be done for the scalar perturbation.
Is there any scenario in which this would be really interesting?
This one probably, because if there is such a big excitation of the scalar perturbations, I may need to worry about their back reaction into the matter field dynamics. And in phase transitions, in any circumstance where you have instabilities that are in the matter field sector that are capable of translating into instability of your metric perturbations. So yeah, I think, for instance, in axial inflation, people have studied reheating, and they claim that the production of gravitational waves is so large during reheating, they can put bounds in the coupling between the axion inflaton and the FF dual term based on saturating NF bounds. Okay. However, that's based on the lacking of back reaction of those gravitational waves into the expansion of the universe and the matter field. So that would be an interesting exploration. Yeah, it has to be done, but again, it requires a lot of time, you know. But one message, since you guys are asking about different things that I could do or not, is that you know, if you want to learn more, really, the idea is to study the code or put your students to do it, no? But since I understand this is a difficult task, it takes a lot of time, we've initiated a series of schools. And essentially, a month ago, we did the first school in Valencia. I think successful. We got like over 40 people coming from all over the place. And the idea is to do a series of schools in principle periodically. These are not just meant for PhD students, they are meant for any researcher who wants to learn how to do these techniques, which unfortunately are not typically the things you learn in your master degrees, no? And, well, keep an eye if you are interested in learning, because we are organized most likely online, the 2023 school, and within 4 days you can learn essentially everything, how to use the code. You know? Doesn't mean you are going to be able to explore everything immediately after, no? But This requires practice, but this is certainly one message I want to give you, that the idea of this code is that people who are not experienced with this kind of calculations, you guys start moving forward into this direction.
I got just one quick question. Can you briefly comment on the Schwinger production that you mentioned?
So people have studied that in action inflation. You have a beautiful analytical formula here. When you integrate out the fermions you are producing, you have this beautiful formula that tells you introduce a current proportional to the electric field you have, where the proportionality is the conductivity, and this contains the information of the production of your fermions. And there are analytical expressions that people have been using in these studies of action inflation. And what I'm saying here is now we are going to be able to do this fully homogeneously and see what's the impact of that. And also, of course, maybe we will try to do something better than using this analytical expression for the conductivity. Yeah. That's it. And the importance of this kind of fermions is that if you couple them with the action, the problem is that they block the excitation of the gauge field as much as we want, So it's very relevant to study that case, because, for instance, if this gauge field is the hypercharge of the standard model, then not only I'm going to have to add also the SU2 sector, I'm also going to have to consider the fact that there are fermions in the standard model, So I think it's going to be a relevant study, and actually we have started that with Mariano Quiros, who is one of the persons who very recently studied this in the homogeneous back reaction regime. Thanks.
Okay, so there are no more questions. Thanks, Danny.
Thank you.